Okay, on behalf of the National Academy of Sciences India Delhi chapter and MHRD Institution Innovation Council, Deen Upadhyaya College, I welcome all of you and the attendees and Professor Smith in this webinar series by distinguished experts. Today we have Professor Chris Smith, and he'll be talking about on the can future energy needs be met sustainably. Professor Smith, he's a theoretical physicist and is currently interested in all aspects of energy supply and demand. Most recently, he was Director of Energy Research, Oxford University from 2011 to 2017, and President of the Council of CSAM, that is Synchronotron Light for Experimental Science and Applications in the Middle East, from 2008 to 2017. He has served as Chair of the Council of the World Fusion Energy Projects ITER, Director of the UK's Fusion Programme, Provost and President of the University College London, Director General of CERN from 1994 to 1998, when the Large Hadron Collider was approved and construction was started, and the first chairman of the Oxford Physics, that is from 1987 to 1992. Professor Smith has written and spoken widely on science funding, international scientific collaboration, and energy issues, and served on many advisory bodies, nationally and internationally, including the UK Prime Minister's Advisory Council on Science and Technology from 1989 to 1992. His scientific contributions and leaderships have been recognized by awards and honors in 7 countries on 3 continents, including election to the Royal Society in 1984, a knighthood for services to particle physics in 2001, and most recently, the award of the Royal Society's Gold Medal in 2015. On behalf of the Dayal Upadhyaya College and NASI Delhi chapter, I welcome Professor Smith, and I request him to kindly share his screen. Yeah, you can share your screen. Yeah.
Can you see me?
Yeah, I can see you. Yeah.
Fine. So good afternoon, everybody, and I hope the air quality is all right in Delhi today. I'm going to say something about air quality when I discuss sustainability later. Now, I'd like to show you my slides, which are coming up now, I hope. Yes, get into slide view. Where are we? Okay, is that clear, Manoj? You can see it?
Yes, sir. We can see that.
Good. So my title, as has been said, is Can Future Energy Needs Be Met Sustainably? And this is really 2 questions. One is, can we meet future energy needs at all? And can we meet them sustainably? And the perspectives on this problem look extremely different in different parts of the world. And I want to start by saying something about that. So on this slide here, on the vertical axis is what's called the Human Development Index. So this is a measure of the quality of life, which is a mixture of life expectancy at birth, the level of education in the country, and national wealth per person. And up at the top is supposed to be in blue, very high quality of life, 1 is the maximum, and down at the bottom, very low quality of life. And you see India sitting here in the low quality. But on the other axis here, this is the amount of energy use per head, per person. This is measured in kilograms of oil equivalent. So that's to say, if all your energy came from oil, doesn't, 2,000 here would mean that for each person's would have to burn 2 tons of oil a year. And what you see here on this plot is that as you go up in the quality of life, you tend to need more energy. So more energy seems to be needed, some curve going up like this, to produce a better standard of living. Well, that will be fine, apart from the fact that as you go up, you seem to need produce more carbon dioxide. And that, of course, is a real problem, because it's not just that we need to have less carbon dioxide. As I will explain, a sustainable planet requires not just that we slow down or have a small amount of carbon dioxide, but we go to zero emissions. So the challenge is for countries like India that are wanting to move up and somehow move to the left, and for countries like mine here to move down to zero. So if we look at what's happened, well, here's what's needed in green. We need to move down here. But unfortunately, Manoj, your picture is obscuring my view. I don't know how to, I can move it down here. That's better. We need to get down to here. Now, what's happened in India from 1990, the Human Development Index was down here, about 0.43. Today, it's about 0.63. So India is moving up, but it's following this expected curve to give better standards of quality of life, needs more energy, and you're getting more energy. That's fine. But the problem, of course, is at the same time, you're going up in carbon dioxide. So somehow we need to get India and these other countries here on a trajectory curving to the left, and countries like mine up here moving down towards zero. Now, before I come to the necessity of getting to zero and how it might be done, let me say something about where energy comes from. For some reason, this doesn't want to move to the next slide. Here we go. So I've moved too far. So this is primary energy use. So this is a split of energy in the world and in different countries. And you can see that in most of the world, about a quarter of the energy comes from coal on average. But India is an outlier, using much more than a quarter, and China even more so. And that's responsible for the fact that producing rather large amounts of carbon dioxide relative to the energy use. And that's because coal produces the most energy, most carbon dioxide per energy, followed by oil, followed by gas. The other thing that we notice here is the UK is practically out of coal, although we were the first country to get into it in the Industrial Revolution. And the other thing we notice is a tremendous amount of bioenergy and waste here, and energy produced from waste. This is cooking, producing energy needs in the villages in India. Now that's total energy. When people talk about energy, the popular people seem to think that energy is all to do with electricity. But in fact, when we look at energy use, it's everywhere, except possibly in China, electricity constitutes less than a quarter of energy use. So it's very, very important to remember that. Although, as we move away from fossil fuels, the use of energy will increase. So I expect this electricity sector to become bigger in the future. So electricity is a relatively small sector. In other things we can see in transport, the USA, very big, lots of cars, and cars that use a lot of gasoline. A lot of cars in the UK, but more efficient cars, so we don't use so much in transport. And then we see this huge sector of industry in China, and these other sectors generally, a lot of that is to do with heat. So while most talks about energy focus on electricity, and indeed we're going to have a lot more electricity in the future, we must remember that a lot of our energy is in the form of heat today, and that is very difficult to decarbonize. So let me have a look at where the electricity comes from. So this is electricity production, and in India, mostly coming from coal. That's true also in China. In the UK, and I'll show you again this later, we've almost got out of coal altogether. In the USA and UK, relatively high proportion of nuclear. But let's look at the non-carbon sector. So in India, that's nuclear, hydro, and much of this other. The UK is sort of ahead of the game here. In the low carbon sector is now over 50% of our electricity production, and growing very rapidly. We have more offshore wind than any other country in the world. Now, what are the things that drive energy policy? First of all, security of supply. Obviously, It's a priority for governments to make sure there is enough energy to meet needs, ensure that the lights stay on after dark. Is there enough petrol to fill up your cars? Cost, very, very important. Do energy prices foster industrial competitiveness and development in the case of India? And finally, the clean environment. Does the system minimize pollution? And what does it do? What are the health and climate impacts? Now, it's very difficult to meet all these goals. So generally speaking, some trade-offs are required. So if you have to make compromises, this means it's a highly political, economic, and social, as well as a technical issue. In practice, security and costs are mainly what's driving what's happening in most countries. Actually, the trade-off is getting easier because as the cost of the low carbon alternatives, wind and solar in particular, and I'll have a lot to say about them later, as the costs of wind and solar go down, it becomes easier to meet all these goals. Now, I want to say something now about sustainability. And the keys of sustainability is reducing or removing the use of fossil fuels. So I'm going to talk a little bit now about climate change, about which you've probably all heard a lot. So this graph on the left here shows you from 1900 to today, the global mean temperature, that's in black. So that's just a measured value. Now this in blue are models of what would happen without the man-made production of carbon dioxide. So the light blue is a very large range of models, and the heavy blue is the sort of center of gravity of a large number of models. And you can see that there's a natural variability, and that's because the output of the sun, the luminosity of the sun is not a constant, it varies, and particularly it's because of volcanoes putting muck into the atmosphere that blots out the sun. So we would expect the temperature to vary even without carbon dioxide. But in fact, the variation, as you can see, is much bigger. And energy use, temperature has gone up about nearly a degree or over a degree since the beginning of this period, whereas the natural causes would stay, it stays more or less constant. In the orange, that's an ensemble of different models, the light orange, and the red is the center of gravity. And you can see that when you add the models, when you add the man-made carbon dioxide to the natural, this is the sum here of the man-made carbon dioxide and the natural variability, you get a rather reasonable fit to the data. So it's pretty clear that carbon dioxide is causing a temperature increase and that we understand that. And that's having impacts. For example, sea levels are rising. I'll come back to that in a minute. So this is one reason to remove fossil fuels. The other, of which, as you're in Delhi, you're very, very well aware, is air pollution. Now, according to the World Health Organization, air pollution causes about 7 million deaths a year. That's out of a total of 55 million. So that's about 13%. It's a large number. This is from outdoor pollution and indoor pollution. Now, I am aware that 4.2 plus 3.8 is not 7, but that's because there's some double counting in these numbers. And these deaths, about 30% of all deaths, on average, people who die from things that can be traced for air pollution, their life is shortened by maybe 10 years. And here are the average numbers, and India top of this rather unfortunate league table. But you can see, although this is a very serious problem, as you in Delhi know very, very well, in India and in China, it's also a serious problem in the UK and in the USA. These numbers are very uncertain, but when I look at the literature, alternative numbers that I find are mostly bigger. And whenever I go back to the literature, the numbers seem to have got larger. Now, I want to now talk a little bit about a little bit more evidence for that climate change is happening. Well, you see here, when you look at the atmospheric temperature, it's very variable. So it jumps around, and if you're a skeptic, you might say, well, we don't really understand it, although I think we do. But when you look at the heat that's going into the ocean, which is causing the level to rise, you find that it's much smoother because the air temperature jiggles around, but it's bigger than the sea temperature, and the transfer to the sea temperature is fairly steady. So this I find extremely convincing. People have gone around the world measuring the temperature of the sea at different depths, and they've made this graph here. And you see if they set 0 in 1995, I suppose that is, it's gone steadily up. So we see here a rather steady and convincing rise in the sea temperature. And then there's lots of other evidence. Forest fires in the USA, for example. Back in the 1980s, there were about 140 major fires every year. In the first decade of this century, more like 250. And the period in which they happen has got longer. And this is because the snows are melting sooner, the dry period is longer, the temperature is higher, so there are more fires. Some of this is because of human settlement, taking over, and so on. But most of this is due to climate change, and it's going to get worse in the future. Now, the trouble with this is it's bad enough as it is, but there could be tipping points, points where we really get into a catastrophe. So if we look at the sea level rise, the rise that's happened, which I showed you before, wait a moment, I'm going in the wrong direction. Back here, you see some sea level rise. That's mostly due to increased runoffs, melting of glaciers, and secondly, to the expansion, the thermal expansion of the sea. But there is a contribution, today a bit less, from the melting of the ice cap in Antarctica and Greenland. But it's quite possible that that could speed up. And there are people who think that that could lead to a rise of sea level by 2 meters by the end of the century. The people who say that, here's one reference, say the probability of getting a 2-meter rise is extremely small, maybe 10%. But the risk is enormous. If a 2-meter rise would flood the Nile Valley, put much of Bangladesh underwater, New York, London, Shanghai, etc. So there can be tipping points. Another tipping point is in the release of the changes in the permafrost. So the frozen areas in northern Canada, in Siberia, are gradually thawing, and they are emitting CO2 and methane. And I'm going to come back to methane in a moment. I happened to be in the University of Guelph last year, and so I put up this reference. And these guys from Guelph think that this effect, just from thawing, could be twice as big as already taken into account in models. And it could give another 200 gigatons of carbon dioxide by the end of the century. Is this a big number or a small number? It's big, because as we'll see in the moment, the International Panel on Climate Change thinks that to limit climate rise, temperature rise to 1.5 degrees, we cannot burn more than or produce more than something like 580 to 770 gigatons of carbon dioxide. And it's worse than that. These people think there could be tipping points, situations like that in this photograph, where you get abrupt thawing, where part of the permafrost collapses, which could add another 100 gigatons. So there is a big danger of tipping points. Now I want to come to an absolutely key point, which is that carbon dioxide emissions have a permanent cumulative effect on temperature. So, and this is the reason why we have to go to zero emissions. So let me look at these 3 graphs here. First, business as usual. So this first graph is billions of tons emitted per year from today at about 40 billion tons of carbon dioxide and carbon dioxide equivalent, and it's rising more or less linearly. But when the carbon dioxide gets into the atmosphere, it tends to stay there. Let's look what would happen if you turned off carbon dioxide emissions. this level will go down. So you stopped at this point today. It will go down very slowly as some of the carbon dioxide is taken up in the atmosphere, in the oceans. And after with a time constant of 250, 300 years, there will be new equilibrium between the atmosphere and the ocean at maybe some level down here somewhere. But it's a slow process. And then after that, to get back to pre-industrial levels, you'd have to wait tens of thousands of years for rocks to take up the carbon dioxide. So that's if you switched off. So the carbon dioxide is going out of the atmosphere, but very slowly. If you keep on putting it in at a constant rate, the amount in the atmosphere, if it's going up linearly, will go up quadratically, more or less. And that will lead, if you just go on doing it, to a linear rise in temperature. Now, what would happen if you switched off to the temperature, if you switched off carbon dioxide emissions? Well, there would be two conflicting effects. First of all, today, because of the carbon dioxide, less heat can get out of the atmosphere than is coming in from the sun. So the Earth is not in equilibrium. If we switched off emissions, it would not suddenly go into equilibrium. So if we just switched off emissions and nothing else happened, the temperature would tend to continue to rise. And it would continue to rise until the extra heat in the atmosphere was taken up by the oceans, again, with a time constant of 250 years or something like that. So because we're not in equilibrium, if we switch off emissions, the temperature will tend to go up. On the other hand, the CO2 is tending to go down. So that will mean the imbalance changes. So that will be a tendency for the temperature to go down. So there are two opposite effects. If we switch off CO2 at this date, the temperature tends to go up because we're not in equilibrium, but it tends to go down because CO2 emissions are going down. These are happening on the same time constant, and it happens they're numerically essentially equal. So if we switch off emissions, it's expected from all the models that the temperature, with a little bit of uncertainty, would stay more or less constant. What that means is that if we want to limit the temperature, it's not enough to slow down. If we go on emissions, the temperature will go on going up, maybe more slowly, but it will go up, and eventually we'll reach some catastrophic point. If we want to stop, we must stop altogether or take carbon dioxide out of the atmosphere. And here is the budget that I mentioned before. Now, let me say a little bit about methane. I mentioned before that when we look at the tundra, when it melts, it's releasing carbon dioxide, but it's also reducing large amounts of methane. Now, methane has very, very different effects from carbon dioxide. In the literature, you can read the phrase of the carbon dioxide equivalent of methane. That's extremely misleading. They are in no sense equivalent. So let's look in this left-hand graph. If you emitted a pulse of carbon dioxide, 1,000 gigatons, just a sudden pulse, and 10 gigatons of methane. And the effect here on the temperature for the first 10, 20 years will be identical. In other words, the methane, for 1 ton per ton of methane, it's having 100 times bigger effect. Methane then goes out of the atmosphere. Actually, some of it, methane alone is on the dotted line, but while in the atmosphere, the methane, some of it goes into ozone and water, which is also greenhouse gases. So the effect of methane will go down. So if we go to 100 years, the difference here is this is a log scale, is about a factor of 3. So whereas back here, the temperature rise of 1 ton of methane will be equal to 30 tons of carbon dioxide, 100 tons of carbon dioxide. After 100 years, it's about 30 tons. Now, unfortunately, in comparing methane and carbon dioxide, a convention has arisen to look at what happens after 100 years. So people quote the carbon dioxide equivalent of methane as being a factor of 30. But in 100 years, we'll all be dead, and the Earth may have passed a tipping point. So actually, we should be taking a much bigger factor. So it's very, very serious what's going on with methane, and we need to find ways of getting it down. That's for a pulse of methane, steady emissions. To begin with, if you just start at this point, a steady emission of carbon dioxide, a steady emission of methane, the temperature rises linearly with carbon dioxide. This is a factor of 10 difference here only. With the methane, it goes up much faster, but then the first bit dies down, the second bit dies down, and gradually it smooths down, and the carbon dioxide eventually overtakes. But the point that I want to make is that methane is very, very dangerous for the climate, and that comparing it with a factor of 30 is potentially very misleading. Now, what is the world doing about this? Actually, maybe I will pause there and ask if there are any questions. I'm not quite sure.
Yes. Yeah. Am I audible to you?
Can you repeat to me if you have any questions, Manoj?
Yeah. Am I audible to you?
Yes, I can hear you.
Okay. Okay. So I'll take up. There are 3 questions.
Right.
First one is by Gauri Sharma. How can we remove carbon dioxide from the atmosphere?
Okay. I'm going to talk later about how to pull carbon dioxide out of the atmosphere. So I'll come back to that.
Okay. Okay. I'll take up the next question. Why air quality index values are different for various countries across the globe? Why not they are same all over the world?
Yes, it's very difficult because the air quality effects depend on the nature of the emissions. So I think these air quality measures are extremely crude. I think all we can say is it's a very, very serious problem, and particularly for India, of course, for Delhi.
So these are the only 2 questions as of now.
That's it?
Yeah, there is one more. One more has just come up. Apart from the industrial and other non-industrial domestic users, what is the percentage contribution of total accumulated respiration of the global 700 plus billion population to total carbon concentration in the atmosphere?
I mean, the carbon concentration in the atmosphere today is extremely small. It's about 420 parts per million. And that's why it's extremely difficult to remove it from the atmosphere. I'm not sure I understood the rest of the question.
Yeah, so that's why they blow. Yeah, yeah. So he's just trying to ask that in comparison to the way we breathe, and when the carbon dioxide, what is being exhaled outside. So how that percentage contribution is there if we are talking about the overall global scenario?
Well, I mean, we are putting the pre-industrial level was about 350 parts per million, and today it's going up a few tens. It's 2 or 3 parts per million per year. So I'll show in a minute how soon we will reach the limit. Okay.
Okay. Okay.
So now, what is the world doing about this? So in 2015, an agreement was reached, an international agreement, which was accepted by all but one country. Now, when I say that, people immediately think it's the USA. That's not true, actually. The USA accepted the agreement, but it hasn't yet ratified it. The one country that did not accept, if it's a country, is the Vatican, actually. So it's a minor player. Every country in the world agreed in Paris, but 19 countries have not yet ratified the agreement. Those 19 countries are responsible between them for 11% of emissions. And one of those is the USA, which at least President Trump, and he may not be there for very long, says that the USA is going to leave the agreement. Now, the agreement was to try to hold the increase of temperature to 2 degrees. That will be very, very difficult. And even more ambitiously to 1.5 degrees. I'll show you how we're doing in a moment. And to try to reach zero emissions or a balance between emissions and taking out of the atmosphere in the second half of the century. The agreement is voluntary. The countries volunteer what they would like to do. If we look at the pledges that have been made, they're nothing like enough. Even if they're all met, what's on the table today, we're still going to get by the end of this temperature something like the century, something like a 3.5-degree temperature rise, which will put us in a very, very dangerous regime. The monsoon may change, for example, have really serious effects, obviously, for India. So they're not good enough. On the other hand, if it wasn't voluntary, they would never have reached an agreement. So the fact that there's an agreement is a good thing. Does the fact that the US may withdraw matter? Yes, but it's not critical, because actually in the US, the energy policy is mostly controlled by the states and not by the federal government. And many of the states, California, for example, have very strong climate policies, which they're not going to change even if President Trump is still there, whatever he does. But it does weaken the pledge of the richer countries to help the poorer countries finance decarbonisation. Obviously, without the US, a very rich country involved, there will be less money on the table. Now, the Paris Agreement did not apply to international aviation and shipping, both of which are substantial contributors to emissions, and they're going up, aviation in particular. But there are now agreements on those things, but they're very difficult. Now, the world is not on track. So this graph here on the left, I'm trying to find my cursor, here we go. The graph on the left here, these are carbon dioxide emissions. And let's look, when the first climate agreement was in around 1990, here we are today somewhere. And despite the agreement, if anything, carbon dioxide is accelerated. And that's, of course, because of development in India and China in particular, using more energy. So we are not on track. If we look per capita, some of this increase is, of course, because rising population in India and China, but the per capita emissions are also going up. If we look at the CO2 emissions from different parts of the world, from 1990 up to today, in the richer countries, those that belong to the Organization of Economic Cooperation and Development and the European Union, emissions are beginning to go down, but the rest of the world, they're going up. Now, you have to be very careful. These are emissions, annual emissions, but if the emissions are going up linearly, since the amount in the atmosphere accumulates, it's going up quadratically. So don't say, oh, well, this is not so serious. The slope is not very high. The amount in the atmosphere is going up faster. Now, how can we decarbonize? I'm running out of time already, I realize. How can we decarbonize? We can reduce demand now for energy. That means planning cities so that we build cities where it's possible to walk or to use bicycles. I've been in American cities where it was more or less impossible. I was in Dallas once and I wanted to go to a shop, and the people in the hotel said, I asked, how do I get there? I said, I'm going to walk. I said, don't do that, you'll be killed. It's impossible to walk in this city. We need to plan cities so that they are compact, so that there is a lot of public transport and so on. And the changing lifestyles will help. We must use energy more efficiently. That is essential, but it won't solve the problem. It's happening that the rise of energy and carbon dioxide and gross national product, I don't have time to discuss these graphs, they're decoupling, but not fast enough. We could do much better technically, but it's very hard. And the reason is that if you make, the main reason is it's to do with what's called the rebound effect. If you make energy use more efficient, then unless you put up the price by adding taxation, energy becomes cheaper. And no government wants to put up the price of energy. So if you make energy cheaper, if you make anything cheaper, people tend to use more of it. Now, for certain things, they don't use more. They already have enough. But if the energy they're paying for becomes cheaper, they have more money in their pocket. So they spend it on something else, and that uses energy. That's called the indirect rebound effect. So simply making energy use more efficient is not going to reduce the use of energy. We've got to have regulation. And that works. And it turns out that around the world, increasing sectors are increasingly subject to regulations, stronger building regulations, stronger regulations on the performance of cars, stronger regulations on industry. And the other thing we have to do, of course, is to move to low carbon systems and sources and possibly negative emissions. So I want to talk now about low carbon systems. And I'm going to look at what I call the stubborn sectors. Those stubborn meaning very hard to decarbonize. So I've put up here all energy sectors, and in black, I've got the ones that are very hard to decarbonize. So the first thing to remember is that I said before, the energy, final energy is 50% in heat, 30% in transport, 20% in electricity globally. I didn't show them the global numbers. Primary energy is a bit different because electricity is produced by burning fossil fuels. And those of you who are scientists know that because of the second law of thermodynamics, that's very inefficient, typically 35% efficient. So electricity takes a much bigger share of primary energy. Transport is somewhat bigger share because energy is lost in refining oil. So when you put in the inefficiencies, roughly the call on primary energy of heat and electricity are the same, and transport is coming in third. So the big challenge is decarbonizing industrial heat. We need to capture CO2 that's currently vented. For example, in making steel and cement, it's done in steel mostly by heating up iron oxide with coke and makes iron, and the carbon dioxide is just left into the atmosphere. So that has to be captured, or we have to use another element for reducing iron oxide, hydrogen, for example. That currently is more expensive if you want to make what's called green hydrogen by electrolysis, but it's possible. Or to make high temperature industrial heat, rather than burning coal, we need to burn hydrogen. So that's very difficult. Decarbonizing space water heating and cooling is important, not in my country, but in countries like India. That takes about 50% of the energy that goes into heat or cooling. That depends on the location, so I won't discuss it. But again, hydrogen can matter. Transport, light vehicles, they'll probably become electric, but some will be maybe in hydrogen fuel cells. But they are not in black because we know how to do that in principle. Heavy vehicles, batteries don't work so well, they're just too heavy. So that's going to be powered by hydrogen or ammonia, maybe burning ammonia in turbines, and maybe electrical pickup from outside. Shipping, the agreement, which I didn't discuss, implies that most new ships built by 2030 will have to have zero emissions. Today, there are no large ships that have zero emissions. So there's going to have to be a revolution in shipping. They're going to have to be powered by hydrogen or probably more likely ammonia. Again today, aviation is entirely producing carbon dioxide. We're going to need, for short distance, maybe electric planes, but the batteries are too heavy for longer distances. We're going to need biofuels, perhaps ammonia. Now, electricity I did not put in black because it's easy to, in principle, to electrify, to decarbonize electricity. We move to nuclear, we move to wind, we move to solar. But as we increase the electricity demand in heating, in vehicles, in marine and aviation, and in making hydrogen, the demand will go up. So it's a moving target. And in the long term, if we use a lot of wind and solar, we're going to need to be able to store it for use when the periods when the wind is not blowing and the sun is not shining. And the best way to do that for long terms is turning power into hydrogen. Now, I put a star here, and that's because these transport and heat are much more people sensitive than electricity. If you put a plug into the wall to buy electricity, it makes no difference whether the electricity that's supplied is coming from low carbon sources or high carbon sources. There aren't green electrons. The electrons are the same. You don't care. You don't have to change your lifestyle. On the other hand, if you change the way you heat your house, or you change the way industry provides heat, or if you change how you fly or go by ship or what sort of car you have to change your lifestyle. So that's much more sensitive than electricity. Now, I'm out of time, so I won't go through a little bit more of that. Oh, except to say that what's called the circular economy is going to get very important. We need to find ways to recycle, to reuse waste, and to change our lifestyles through car sharing and office sharing. And in the EU, it's thought that what the energy used in steel, plastics, aluminium, and cement, in principle, could be reduced by about half by 2050 if we get into car sharing, office sharing. The lockdown is causing less car use and probably less use of offices, using products more efficiently, and recycling. So there's a big, we shouldn't only think about the technical approaches of how to make cement and so on. We ought to think about ways of reducing use. Now, on this previous slide, I've skipped here. You saw hydrogen, 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 ammonia, 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 ammonia. So I want to say something about hydrogen and ammonia. So they have many previous uses. Comparing them, ammonia is made from hydrogen. So if you want to make hydrogen, green hydrogen without CO2, the ways to do that, at the moment, hydrogen is made by heating up methane, natural gas, and simply letting the carbon dioxide go into the atmosphere. So you have to either capture the carbon dioxide and store it, but then it's not perfect carbon dioxide capture, and there are methane leakages. So that's not a very good way to go. The best thing to do is go through electrolysis, but then you need green power. If you use electricity, which is produced from sources that are not carbon dioxide free, the hydrogen won't be carbon dioxide free. But in the long run, electrolysis today is more expensive than steam methane reforming, but it's going to become cheaper. Once we have green hydrogen, we can make green ammonia, because ammonia is made from hydrogen. And making green ammonia is an important objective in its own right, because ammonia is used in fertilizer. It produces nearly 2% of the world's carbon dioxide. So we really have to, regardless of everything else, move to green ammonia. Now, I don't have time to go into that, except to say something about the scale, to show you that this is something which is on the scale we want. If we took current ammonia production produced to give fertilizer, and we turned it, instead of producing fertilizer, we turned it into electricity, it would produce the whole of the world's electricity supply. If we did it with 50% efficiency, it would produce all the world's power for 7 days. So if we doubled ammonia production, the extra ammonia, if we doubled production, would be enough to produce the world's electricity for 7 days. So these are potentially very big numbers. And it's starting to be taken very, very seriously. On the 7th of July, just 4 days ago, an agreement was produced for a hydrogen-based ammonia production facility in Saudi Arabia, powered by wind and solar, to make electricity to go to an air separation unit, which is needed to make ammonia, and to make hydrogen. And then in ammonia production, the Haber-Bosch process, nitrogen and hydrogen are combined. Ammonia is easily transported. It's a liquid at 10 atmospheres or at minus 33 degrees, so it's easy to liquefy and transport. Unlike hydrogen, which can only be liquefied at extremely high pressures or very low temperatures, then it can be transported, it can be stored, and then they're imagining that the use is by separating the ammonia into hydrogen and putting the ammonia into buses and trucks. But you can do other things. You could put the ammonia, you could burn it directly, or you could put it into fuel cells to make electricity. Now, I will finish with a few brief words on electricity, because I think I've only got 5 minutes. Is that right, Manoj? Coming up.
Yes, sir. Yeah, 5 to 7 minutes.
Okay. So if we look at electricity use around the world, we see that it's going up. And we see that it's mostly coming from coal, it's going up, from natural gas that's going up, oil going down a bit. So the world is becoming increasingly electrified. So fossil fuels are going up and they're set to remain dominant in the near term. So that means if we're going to use fossil fuels, we've got to capture the carbon dioxide and store it. But carbon dioxide is not perfect. 10% or so leaks. And if we include the methane leakage, it's not really satisfactory. So I don't believe that this will play, or shouldn't play, a large role in power generation. Instead, we're going to have to move to wind, solar, nuclear, and hydro. Hydro, the expansion is limited around the world. We're already having a lot in India. Nuclear can be expanded, but the big hope is that wind and solar can play a big role. The problem is, if we look from 1990 to today, wind and solar together are about here. So the question is, if we go 30 years from the past, from nothing to 30 years, they've come to something like here, can they go up to meet a meeting target in the future? And the answer is, there is enough, and the cost looks all right. The difficulty is that wind and solar cannot be controlled. For example, if the wind blows mainly at night, it may be cheap, but it's relatively valueless if nobody wants it. On the other hand, if you install enough wind energy to meet the average demand, there will be times when there's too much, at night, for example. And that will put up the cost because you'll be using things that producing wind energy that you don't use, unless you store it. But storage is very expensive. So the cost of using a lot of wind and solar will increase as contributions increase. We're going to need flexible backup for when the wind does not blow, the sun does not shine. It's going to be very expensive, this backup, because as wind and solar get bigger, it won't be used. We need to shift demand to when the wind and sun is blowing. We're going to need storage, and we need ways to design the system to minimize the cost. I think I'll just talk about the cost of wind and solar and then jump quickly to my conclusions. So this is the good news. So this shows the cost of electricity generation in US dollars per kilowatt hour. These are numbers this year from the International Renewable Energy Agency. And this brown sector, this light gray sector, that's the range of fossil fuel generation costs. In blue here, you see the cost of generation from solar voltaics. That's stopping today or last year. And the brown are the costs of auctions which go into the future. So there's an auction to provide solar energy in 2022, for example, showing up here. And you see that solar energy, in terms of the cost of generation, is now down at the very bottom of the range of fossil fuels. But the value is less than the cost because it's not there at night and sometimes the sun does not shine. If we go to onshore wind, it's been one of the cheapest ways of generating for ages, and it's now also very, very competitive. But the wind doesn't always blow, so it's the same problem. And if we go to offshore wind, and this is extremely important for the United Kingdom because we have a lot of potential for wind in the North Sea, it's going to be our main source of electricity, I believe, we can see that that is becoming competitive also. So on electricity costs, we can compete. I won't talk about the problems of integrating renewables. Let me come to finish with whether we can meet the Paris goals. There is some good news, particularly that the cost of wind and solar are coming down, but it needs qualification. To reach the goals, it's going to have to go on going down. That's sufficient, but not that's necessary, but not sufficient. We need, in addition, the performance of batteries for electric vehicles and to provide day-night storage of solar, and to provide the frequency and control of the grid. We need affordable green hydrogen ammonia for long-term storage, for process heat, for space heat. We need improvements in efficiency, which will come through regulation. We need to move to the circular economy. and we need support for pumped hydro, cheaper nuclear. And we need negative emissions to compensate for the stubborn sectors and countries that are not playing their role, which are not bringing down their carbon emissions. And we need good policies, and we need this to be socially acceptable. And we have to hope for all of these and for things that we haven't thought of. Now, a brief word about negative emissions, because it was mentioned. So the way of getting negative emissions is by growing trees, afforesting regions that have been deforested or reforesting other regions, changing land use, bioenergy with carbon dioxide capture. When you grow biomaterials, it takes carbon dioxide out of the atmosphere. When you burn them, if you capture the CO2 and put it underground, you get negative effect. You need materials that take up carbon dioxide, that can do something. And you need maybe direct air capture. So here's the answer to the question that was asked. People like this company think that with a device like this could produce maybe 1 million tons of carbon dioxide a year. The problem is that we want something like 11 gigatons of negative carbon dioxide a year. So we'd need 10,000 such devices. They're very clumsy devices. I hope we don't have to go to that way. And they're going to be very expensive unless these lower estimates are correct. I'm going to finish with 2 slides. Sorry, I've got back to my backup slides. Let me get here. Yes. Meeting the Paris goals will be difficult, but not impossible. There's a long way to go. In the near future, the route is clear. Anything that can be deployed at scale must already be there. If it's going to be deployed at scale in the next 15 years, it's not still in the laboratory. In the longer term, it's less clear what will happen. Cheaper nuclear, moving to long-term storage, enabling 100% renewables, relatively inexpensive negative emissions. But it's going to depend on the political will to introduce carbon pricing, reorganize the markets. Countries need to adopt strong climate targets, ours has, and those that have done so, like the UK, now need to focus on how to give them. The good news is that technical developments now have momentum, which could put us at a tipping point. I can imagine a world in the future mainly provided by over-provision of cheap wind and solar, supported by storage, cheap nuclear, and hydro in countries that have it. Can we have a tipping point? So this is my last slide, which I don't seem to be able to get to. Here's my last slide. So this is a picture of New York in 1900, and you see lots of horses and buggies. There is one car there, ringed. If we go ahead 13 years, we see lots of cars, and we see one horse and buggy. So this was an incredibly rapid transition. So rapid transitions are possible, but we shouldn't take too much comfort from this slide, because a car is enormously better than a horse and buggy. So there's tremendous incentive to trade in your horse and buggy for a car. If we want to move from these cars to electric cars, in some ways they're less convenient. They can't go so far. So we don't have the same incentive. So this is not necessarily a good analogy. The only way to make the fast transition happen is to make the move to electric vehicles and other low carbon alternatives cheaper than what we have at present. And I think that can be done. Is it going to happen? Can we meet future energy needs sustainably? I think the answer is certainly yes in principle. Will we? I think probably in the long run, but not as soon as we would like. Now, I get asked, am I an optimist or a pessimist about this? Now, there is a rather cynical definition of a pessimist, which is that a pessimist is an optimist who is properly informed. Now, I believe that I'm properly informed, but nevertheless, I am an optimist. And I'm an optimist because I think that necessity is the mother of invention. as the effects of climate change become more apparent, and effects like air pollution get more into policy making as they are in Delhi and in Beijing, I think that the world will manage to decarbonize, albeit not as soon as I would hope. Thank you very much.
Thank you very much, Professor Smith. I must appreciate all the attendees, and this has crossed 400. I would like to share that part. 400 attendees in this talk, and especially because in India this is usually a lunchtime, and I have never in my career have seen 400 plus attendees during the lunchtime itself. So thank you very much. So there are a few questions, and I'll take up one by one. The first one is by Devaroop Roy, and by Veena Salvi. How do we break our own habit of using plastic?
That's a very difficult question, and I don't know the answer to that. I'm not an expert on plastic, but I mean, one of the things we have to do is make biodegradable plastics, and we're going to have to find a source. They're made from fossil fuels today. So we're going to have to find a source of alternative sources. These could be from certain plants, CAM plants, for example, are quite promising. I'm afraid I wish I knew the answer to that question. I don't, but it's a very, very good question.
The next one is by Yukta Tomar. How much time will it take to stop consuming energy from coal, and how easy or hard it is to switch to other alternatives?
I think, let me say something that I can say with pride about my own country, which is that we have switched from coal. Quite interestingly, in 2016, the last year for which I have a reliable number, the United Kingdom used 16 million tons of coal. That's the same level we were using in 2018. That's over 200 years ago. So we were the first into the Industrial Revolution. We got up to 150 million tons a year. We are now down but the level of 2018. So it can be done, but it's very difficult because burning coal is a cheaper way of making electricity. So that's very hard. And I think the only way we can do it is to find substitutes, which means bringing down the cost of solar and wind. But they are not really low enough today, and that has to be accompanied by storage. And you have to have the resources. The resource is not there everywhere.
The next one is by Meena Mishra. What is the future of semiconductor industry in power generation?
Right, well, I'm not an expert on that at all, but it is important in certain areas. For example, if you moving to hydrogen, you have to have electrolysis to make green hydrogen. You need inverters to turn it into AC. So it's a very important part of that and of the management of the energy system, but I'm the wrong person to ask that question.
Next one is by Amujuri Vishwanath. What are the methods to recycle and reuse carbon for other beneficial purposes?
To recycle what?
Carbon, reuse of
Carbon.
carbon.
Right. Well, there's been a lot of work on that and studies of, well, recycling carbon to make plastics, for example. There aren't many, or using it, burying it in the soil in certain forms, you can enhance productivity while getting rid of it. I actually think there's a lot of discussion of carbon capture and use, but actually I'm not terribly enthusiastic. The numbers I've seen don't look so promising. And one of the uses is people are proposing making synthetic fuels. So the idea is you would take carbon dioxide at power stations, for example, or just sucked out of the atmosphere, and make synthetic fuels that we used in aviation. So that would get you, when you burn them, they put the carbon dioxide back again. So it's better than just burning oil in the first place. You get a carbon neutral cycle apart from losses. On the other hand, you have to ask, if you bury carbon dioxide, if you capture carbon dioxide, wouldn't it be better to put it underground and make it negative and find something else for aviation? And I think it would. So I think we should not go to these recycling. If we're going to capture carbon dioxide, the first priority should be to put it underground and go negative. And we should really, the priority is to seek zero carbon alternatives for everything else. Not sure we're going to be able to do it, and we have to do it cost effectively.
So the next one is by Sanjeev Agarwal. What is cumulative impact of SLCF on global temperature?
Sorry, of what?
SLCF. I'm also not able to clear what SLCF stands for. Yeah. So I'll take up the next one. That is by Inakshi Sharma. How much of the carbon dioxide can be absorbed by plants for photosynthesis, and hence can green forestation contribute significantly to reduce carbon dioxide?
Quite a lot. I can't give you a number, but for example, the United Kingdom, I skipped a slide on this. It's the law in the United Kingdom that we should have net zero emissions by 2050, as much negative as positive emissions. When that law was adopted a year ago, people produced scenarios that were claiming that it was possible, but they all depend on heroic assumptions. And one of the assumptions is the assumption we will eat 20% less meat. That may happen, but it's not so easy to change people's lifestyles. You, as in India, as a very largely vegetarian country, are in a better situation. But in China, meat eating is going up. And it's not easy for me to see meat consumption going down 20%. But the question was about forestation. It's assumed that the area covered by forests between now and 2050, or trees in the United Kingdom, will go up 30%. So that will be a big contributor, but that's a really challenging target. Let me say this 2050 target of net zero emissions in the UK, I have to say that today it hardly looks possible. Nevertheless, I think it's a good thing, because in 1990, in 2008, we adopted a target of reducing emissions by 80% by 2050. And at the time, I thought that was impossible. Today, 80% looks to me possible. Hard, but possible. So although zero looks to me sort of impossible, I'm encouraged that technical progress makes things possible. So forestation is very important. And the first priority is to stop the deforestation in places like the Amazon, the Congo, no doubt in India as well.
Okay. So I'll take up the next one is by Shreyasi Das. We know that last year, University of Waterloo suggested artificial leaf that turns carbon dioxide to fuel. How efficient are these technologies in removing carbon dioxide from the atmosphere?
Okay, well, I showed you this big negative carbon capture designed by a spin-out company from Harvard, where I said we would need 10,000 of these things to get the negative emissions we want. The artificial leaf is something like that. It's a system which captures carbon dioxide from the atmosphere and then it uses to make things. So it's exactly the same thing in a way. I mean, the idea is with the system I showed would be to somehow use the captured carbon to make things like plastics, for example. So it can be big, but it looks expensive.
The next one is by Ankit Shaw. What is the annual percentage of negative emission of carbon dioxide due to rock weathering and ocean absorption?
Today, the negative emissions, I don't know the answer to that in numbers. I mean, at the moment, the oceans are taking up some of the carbon dioxide, but they're also emitting. So there is a small effect, and I showed that. I showed that if we switched off carbon emissions with a time constant of about 250 years, I mean, that's the exponential decay, we would get down to about 20% of the level today. So the oceans are taking up carbon dioxide. On the other hand, I think as they heat up, they're going to emit more. So that's a rather counter thing. I can't give you a number. I'm not an expert on that.
There are 3, 4 questions, but I'll club two of them. One is by Shivangi and the other is by Ganapati. Can we look up for nuclear fusion as an option in near future? And what is your opinion on nuclear power plants for electricity?
Okay, so first of all, fusion. I worked in fusion for some period, so I know quite a lot about fusion. And when I joined, and my background is not fusion, I'm a high energy quantum field theorist. When I joined the fusion community in 2003, I thought that fusion could compete with wind and solar. I thought these were the two really big low carbon alternatives, as well as fission, although fusion have the advantage that it's intrinsically somewhat safer and cleaner. However, the idea that they could compete is no longer obvious to me at all for two reasons. First of all, the cost of wind and solar has gone down faster than anybody could possibly have imagined. I showed you the curve of the falling cost of solar and wind. No one in their wildest dreams could have thought those costs would go down so fast. On the other hand, in the World Fusion Project, of which India is a member, and I know quite a lot about it, I chaired the council at one point, it has gone way, way over budget. So the estimates of cost on which wind and solar could compete were similar to the cost estimates that went into ITER, which turned out to be much too low. So the cost of fusion looks as if it's gone up, the cost of wind and solar gone down. So they've diverged. Now, of course, ITER is the first of a kind. So that's part of the reason. But part of it is, and part of the way it was managed is to put up the cost. But part of the reason is intrinsically that fusion is more expensive than we used to think. Nevertheless, I think we need to finish ITER to find out once and for all, can we control a burning plasma? Is fusion part of the toolkit in principle? If it is, it still could play a role, but not in big devices like the World Energy Project ITER. We're going to have to find ways to control turbulent plasmas better. The problem is when people first thought about fusion in the 1950s, they thought that the heat would, they could have a device which was 1 meter or 2 meters across, and that would be the heat flow from the center of the walls would be slow enough that you could have a net gain of heat. It turns out that turbulent effects mean that the heat flows much, much faster. So ITER is something like 10 meters across. So it's far, far too expensive. We are learning theoretically and experimentally ways to control fusion of turbulence. If we control fusion, there could be a future. As ordinary nuclear is concerned, I think it's going to be very important. It's very hard for me to see how we can use wind and solar without a large contribution of baseload power from nuclear. The problem is that it's always turned out to be more expensive than people have claimed. And part of the reason for that, in the Western world anyway, is that we have failed to reconcile the idea that we can't competition with the idea that to make nuclear cheap, you have to build many devices the same. So that's a particular problem for countries like the UK, which are wedded to the market philosophy. We've got to have competition. But if you build 5 nuclear power stations, you want competition, means they're all different. And the way to get nuclear down is to build many, many devices that are the same. And that's happening in China. I don't know the situation, I'm not up to date in India. It's happened in Korea. So we have to build them the same. I think that small modular reactors could bring the costs down. But again, the reason that in principle, large reactors are cheaper per kilowatt hour. The reason that small modular reactors might be cheaper is manufacturing advantages of building many things the same. But to find out if that's true, we've got to build many. And the world talks a lot about small modular reactors. There are plans to build 1 or 2 prototypes. But to learn if they're really cheaper, it's not enough to build 1, it's not enough to build 2. You'd have to need 5 or something, identical prototypes. So I think the nuclear, we've got to make it cheaper. And I think that it can also be made more valuable by coupling it with storage, thermal storage. It's very cheap to store heat. So you can store the heat at night, some of the output, say half the output at night goes directly to the electricity grid, the other goes into molten salts, put it back in the day. So you could have a power station which was running, producing 3 times as much electricity at night, in the day as at night. That would put up the cost, but it would put up the value.
So that's the second last question now I'm putting up. Air pollution is increasing over South Asia. That is by Vinod. Are there any understanding about how much of renewable power from wind or solar that we have lost as a result?
As a result of what?
As a result of due to the pollution, which is.
I don't know the answer to that question. So I mean, I've recently made a reassessment of the availability of wind and solar in the UK, and there's far more than we could ever need. So that's reassuring. And I suspect that that's true everywhere. And wind, of course, is not affected by pollution. I think one of the difficulties with wind is we don't know what's going to happen to wind because of climate change. So the variability of wind will go up. Everybody agrees with that. And the problem with wind turbines won't operate above a certain speed. So we may lose some of it, but that's not the question. The question is how much does the delivery at the average speed? I mean, how is the change distributed over the velocity curve? So wind is a bit uncertain, but I'm pretty confident that everywhere, but not necessarily at every time of year, there will be enough wind. There again, we need storage. With solar, I ought to know the answer to that question. I doubt that it's more than 20% or something. I mean, it would be a very big effect if we were using concentrated solar, focusing the sunlight to make very high temperature to drive turbines. But that technology, I skipped over it in the slide about renewable costs because it's proving to be much more expensive than PV. Photovoltaics are becoming much cheaper, and photovoltaics work with scattered light. They don't need direct light. So the pollution changes the spectrum and it changes the peak intensity, but I'm not sure what it does overall. It's probably an effect of 15% or of that order. That's my guess. I honestly don't know the answer.
Okay. That comes to the last question, and that is by Vanita and others. So I'm combining the two questions. Your thoughts on production of green hydrogen by dark fermentation process using waste? And the second is, what is the scope and future of fuel cell as an alternative method of production of electricity?
Yes. Well, but actually, before I answer the last question, let me say I will give you a cleaned up version of the slides that you can put on the web. And I'm very happy for you to put, you
Okay,
asked me for this to
okay,
go on
sure.
YouTube. So I will send you a PDF of the slides so people can look at this because I ran out of time. I always run out of time. I thought it was more important to talk about sustainability than the other things. So on the production of hydrogen, the alternative, indeed, using waste is and fermentation and so on is a good way of producing hydrogen. I'm not an expert on that because in the United Kingdom, it certainly looks as if the most likely ways of producing hydrogen are going to be through electrolysis. So I don't know the answer to that, but it's important and it needs more work on it. As far as fuel cells are concerned, the cost of fuel cells is becoming down, but as of today, it's probably cheaper to convert hydrogen into electricity by burning it. Now, I have to be very careful with that remark because at the moment, there do not exist any turbines that work with 100% hydrogen. There are turbines which work with a certain percentage of hydrogen, but as you bring in hydrogen, the temperature goes up and you get problems with embrittlement and materials and so on. But the industry is rather confident that in the next decade, they will have turbines that will work with hydrogen. And funnily enough, I was trying to find out what cost they will be. And the answer I got was, well, they will be more expensive than turbines burning gas, but maybe by 20% or something like that. Today, fuel cells look cheaper, look more expensive, but there is a lot of work on fuel cells, and particularly there are different sorts of fuel cells. And I think one of the interesting things is solid oxide fuel cells, but they tend to need very high temperatures. And there are technologies which can do them with meaning very high temperatures, 750, 800 degrees. There are companies now, there's one in the UK, Ceres, that make solid oxide fuel cells which will work at maybe 600 degrees or something like that. And I think that's really important. And I can imagine that in the future, the solid oxide fuel cells work at a reasonable temperature become cheaper. So I think that is the way I'm imagining a world with a lot of hydrogen produced with electrolyzers, where the cost is coming down, and then being used through fuel cells.
Okay, thank you very much. So we have overshot by around 15-20 minutes. I initially planned for having a 10 minutes QA, but it has extended to nearly 25 minutes. Thank you very much, Professor Smith. And now I invite Dr. Geetika to kindly give over.
Thank you, Manoj. Am I audible?
Yeah.
Yes.
I, Dr. Geetika Jain Saxena, on behalf of the organizing committee, thank all the participants for attending this webinar on Can Future Energy Needs to be Met Sustainably by Sir Professor Chris Llewellyn Smith. And we are thrilled by the attendance we have. It's over 400. I would like to thank our distinguished speaker, Professor Chris Llewellyn Smith, for this very intuitive and knowledgeable talk. He told us about the importance and urgency of reducing carbon emissions and how these emissions are affecting the Earth in an absolute negative way, leading to drastic increase in temperature. He also talked about the ways to decarbonize the environment. We look forward to hear more of you in the future, sir. I would like to pay my gratitude to Professor Ajoy Ghatak for his immense support and giving us the platform of NASI for organizing these lectures. Thank you again for your attendance. We look forward to joining you again tomorrow for the next talk in this webinar series. And we will be sharing the WebEx link shortly. And please don't forget to fill in the feedback form posted in the chat section. It is also required for e-certification. Thank you very much.
Thank you.
Thank you very much, Professor Smith. Thank you. Any last words from yours, concluding remarks from your side?
Just, I very much appreciated the questions, which were very, very good questions. The fact that I couldn't answer them showed that they were very good questions, probing the limits of my knowledge. I think we all have a huge challenge. And I think that one of the things that makes me optimistic is that young people understand the issue and they've become very interested in it. And they're our hope. You don't want people like me. I can talk about it, and I'm doing some work on storage at the moment, but it's not going to be me who delivers it. It's going to be you people in the audience. Thank you very much.
Thank you. Thank you very much, Professor Smith. So the webinar is over, and I request the attendees, after filling up their feedback form, they may leave the meeting. Thank you very much, all the attendees. Thank you very much, Professor Smith. Thank you.
Thank you, Professor Smith. Thank you very much.
Thank you.